Welcome to the lab tour at the Max Born Institute for Nonlinear Optics and Short Pulse Spectroscopy. We'll see today several of our labs where we work on several related topics. Actually, I am personally a theoretician, but I really like to work with experimentalists and I like to see physics happen in the lab in front of my eyes. If we are lucky with my filming crew today, then we might see it happen.
My name is Oleg Kornilov. I'm the department head of the experimental department A2 at the Division A of Max Born Institute. In this laboratory, we use state-of-the-art commercial laser based on Ti-Sapphire technology. The lasers are pumped by the green solid-state lasers, and the power is so high that the company has to use cryogenic technology to cool the crystal. The laser produces highly energetic and very short femtosecond pulses. To use them for pump probe spectroscopy, we split them in two beams and use for pump and probe. In our case, one of the beam is converted to the extended ultraviolet radiation using the famous high-order harmonic generation method. This method produces very broad spectrum of photon energies, and therefore we use the device called monochromator to select one photon energy to investigate the process of interest. In our experiment with the methyl bromide molecules, we use this together with the 200 nanometer pulse in order to initiate dynamics and then follow it in the pump probe scheme to see how electronic excitation localizes on one or another fragment after dissociation.
The things we are doing today have roots in the earliest 20th century, in the early days of quantum mechanics.
My name's Niels Monsrud. I'm a MEDEA student at the Max Born Institute here in Berlin, Germany. I am currently working on a project to do XUV pump probe experiments on a femtosecond beam line, but we hope to move it to a attosecond beam line in the future. Currently, the buildup of my experiment consisted of 3 separate chambers that we constructed with the help of Milano, Italy. And the first chamber is where we collimate and do the first focusing. We also are able to produce the XUV pump and the XUV probe from a single beam into our pump and probe using a split mirror setup. This split mirror setup allows for a delay in the pulse while also giving us control over how much delay. We then go from the first chamber, which you saw, to the second chamber, which is another focusing chamber. The focusing chamber should allow us to get below 6 micrometers, 6 micron focus into the velocity map imaging chamber. From there, we're able to image large clusters, and also we will begin by imaging more well-known molecules such as C60.
As you know, the beginning of the 20th century has brought us many important discoveries. One of them was the photoelectric effect, the removal of electron by light from an atom, molecule, or a solid. By now, we know that photoabsorption is one of the most fundamental and most important processes in nature. It literally affects all aspects of our life, from vision to photosynthesis to the function of DNA in our bodies. Absorption of photons is done by electrons. They are the elementary antennas for light in every material or a living creature. As you may know, electrons respond to excitations on the attosecond timescale, which is very fast. 1 attosecond is so short that even light, the fastest runner in the universe, can only travel from one side of a small molecule to another side in this time. So, resolving fundamental electronic events on the attosecond timescale is very challenging. This is why we need attosecond pulses. Now, 100 years after the discovery of photoelectric effects, we have the technology to make such pulses and to visualize these fast events. Another fascinating discovery of the early 20th century is the electron spin. Excitation of electrons by light can also trigger spin dynamics. It can change magnetization. The most effective way to interrogate magnetic systems is to use circular polarized light. We do it in another lab. We now have extreme ultraviolet pulses, which are nearly circular, can be generated anywhere from 40 to 70 electron volts, and are also quite short, just a few tenths of femtoseconds. Such pulses are really great. We can use them to track ultrafast magnetization of materials, follow spin currents, time-resolved dynamics in chiral molecules, and look at many other exciting things. Imagination is the only limit.